I owe you guys an apology. I haven't made a video in about 3 months, but I actually have a very good reason for that. You see, back in January, I was sitting here interviewing at this great company that I really liked. I knew I would be great at the job, but all of a sudden they shamelessly rejected me. Yeah, that's right. You know, it was a little bit like you have this girlfriend that you really like and you wanna be with her, and then she dumps you, and then next week you see her out on the street with some random guy who is like poor, ugly, and homeless, and you really start questioning people's decision-making abilities. Sorry about this rant, by the way. Moving on to the topics of today's video, where we'll be rendering this cube that you see on screen. To keep this video concise, I just hard-coded the vertex coordinates along with face colors right in the code for you guys. When we were rendering 2D stuff, we used this render pipeline state class, which allowed us to specify which shaders we want to use on the GPU. To render 3D, we just need to add two more components. One of them is depth texture and another is depth stencil state. Now let's take a look at each of them. Depth texture is basically just a region in memory to store Z coordinate of each pixel. Now this is required for GPU to be able to understand which parts of 3D model are visible on screen and which are not. So for example, take a look at this slide here. We have this cube. It has, let's say, front face which is red and a back face that we can't even see. And so when we project that to a 2D screen, then we should only be able to see a red face if cube is not rotated or anything like that. And so GPU can do it for us as long as we provide this depth texture where it will store Z coordinates of each pixel, and then during rendering it will compare those Z coordinates, and depending on the comparison results it will know if pixel is on front and therefore visible, or it is in the back and it is hidden, or as they say, occluded. In my code I will be just taking depth texture directly from view and just wrapping it in render pass depth attachment descriptor so that Metal can get a handle of that. That's one way to do it. Another way would be to just create a depth texture from scratch in our C++ code, and you can do that if you need. Depth stencil state is basically just a configuration class that we need to tell GPU how to compare two different Z coordinates of two different pixels so that it can understand which pixel is in front and which is in the back. There are a couple of ways to do it. The way I do it in code, as you can see, I specify this compare function less as a depth compare function for depth stencil descriptor, and that way GPU will basically take a look at two Z coordinates of two different pixels, and whichever Z coordinate is lower, then that pixel will be considered to be in front and therefore visible. There are more compare functions. For example, there is this greater function which does exactly the opposite. It will take the pixel with greater Z coordinate and put it on front. To get us started, let's just render our cube vertices with the exact coordinates that we hard-coded on CPU side, and we can use that with this simple shader here. And if we run that, we can just see the front face of the cube as we saw on the slide earlier. And of course at this point you can't even tell that this is actually a 3D model because cube is not rotated or anything, so all you see is just a front face. To make it more interesting, we can add these rotations around X and Y axis as you see in this shader. And then if we run this, we can actually see that this is a cube that is rotating. However, there is a problem there. As you can see, as the cube rotates, the front faces and back faces are being clipped different points in time. This slide here depicts the problem that we have is this clipping. Basically, Metal can only render pixels with Z coordinates from 0 to 1. And in our case, as we were doing these transformations for rotation in shader, we were changing our Z coordinates, and the final values of those, for some of those, were less than 0 and greater than 1. And for those pixels, they were just clipped, not rendered at all. And that's why we saw this artifacts on screen. In order to fix this problem, we just need to normalize whatever final Z values we get for pixels to be between 0 and 1. I have the shader code. There is this simple normalization formula that I use. You can take a look at it yourself in my GitHub repository if you want. And now if we run this again, then we see that our cube is rotating, everything is just perfect and there is no artifacts at all. And as you see, that was pretty easy. We just had to add a couple more components to our CPU rendering boilerplate for metal and we got our 3D glowing. I hope you learned something here and I'll see you in the next one. Thanks, bye.